We're up and running again. Early morning here. I've got 10 more problems to do, and I've listed them here. And I think I'll just, as I do one, I'll erase it. I'll do it right there. Hopefully get this centered and off and running. Here we go. All right, these require a whole bunch of calculations here. None of them hard, but there's many, which means carelessness can creep in. Especially when I'm asking you to do 55 problems in 70 minutes. I'm going to be asking you 120 in 2 hours at the end of the term. So how do we deal with this so it doesn't take forever? Well, we'll put it in columns. So we'll multiply across. We've got minus 5x to the fourth. We've got a negative times a negative is a positive. We've got 5 times 3, 15, x to the 3. Trying to be careful here when I'm talking. Minus 20x squared. Then we look for like terms. I got minus 3x to the fourth. I've got minus positive 3x to the third. And we've got minus times a minus again, positive 18x squared. And now I can add up the like terms, which gets me minus 8x to the fourth plus 18x squared. 18x cubed. And what? Minus 2x squared. Okay, and it's real early here, and I hope I copied down the test question correctly. There we go. And I believe that's our answer. All right, so that takes care of that one. All right, we're going to conjugate. 3 over 6 plus 2i. I'll do the shortcut here in a second. We'll take the long route here. 6 plus 2i. So we'll change the verb tense here. 6 minus 2i over 6 minus 2i. We're just changing the way it looks. All right, so numerator equals 18 minus 6i. In the denominator, we get a cancellation of middle terms. 6 times 6 times minus 2i minus 12i. 2i times 6 positive 12i. Those cancel. I won't do them again. We've seen it enough. 2 times negative 2 minus 4i squared. What did we say I squared was? That's minus 4 times minus 1. So I squared changes the sign of the coefficient in front of it. It becomes positive 4. All right, so that gives us 36 plus 4, which gives us 40. And let's see if I want to kind of do that here. That gets us 18 minus 6i over 40. Everything's even, so you should divide everything by 2. I'll show you how that works. 2 times 9 minus 3i over 2 times 20. I don't think I have to do the 2 times this and then divide by 2. So that should be your answer, 9 minus 3i over 20. And we can get that answer very quickly without having to do all this work if we simply look at the answer. And the answer was, I'll bring it back here, was 18 minus 6i over 40. All right, so how can you get that without having to do all that work? Well, it sure looks like 3 times 16, 3 times 6 gets us that. And 3 times 2i gets us 6i, but if we're conjugating, okay, it's going to get a sign change. So it gets us that. And what happens when I square 6 and I square the 2? I get 40 and then reduce. All right, so there's that one. 4i to the 17 is 4i squared. I think it's better if you do this because you get some rules of exponents practice. Textbook would tell you there's a pattern of 4. I challenge somebody to tell me what it is 5 years after you have to get away from these problems. But I think you've got a chance at, if we overlearn this, you got a chance at remembering that the most important thing is I squared equals -1. And this highlights multiplication of -1 8 times I. Now, if you do that an even number of times, if we do a multiplication once by a negative, we get a negative answer. Twice positive, 3 times negative, 4 times positive, 5 times negative. I'm going to stop there. There's a pattern, and you have to think about that pattern. If you want to make gains in this class, as Mr. Flynn would say, you have to engage in the process. All right, so what do we have here? We have an even number, right? You know, at the start, this, if it's odd, is going to have some kind of I answer. It's either going to be -4 or +4. How do you decide? You've got to write I squared as either an even or an odd to determine. This is even after we do that, which means we're going to get 4i. I don't know how else to explain this. You have to engage in the process and think about it. Now, I will post rapid fire 5 videos. I'm going to start doing those now. You've been exposed to a lot of material by midterm here. And now it's time to hone in on where you're having trouble. So I'll start doing 2 or 3 videos a night, rapid fire 5, where you get, okay, 4i to the 19th. What would that be? Well, it would be 4i squared. 9 times gets me to 18 times 1 more. That's odd. So it's -4i. That kind of practice. All right. And where did I put my eraser? Here it is. And if this had been 18, then that would have been 4i squared 9 times and no extra multiplication of an I. So what does this become? +1 or -1? I hope to God you're saying negative. All right. Next problem. That's done. X cubed equals -216. Here's x squared. That hits +216 twice, right? What's x cubed look like? X cubed looked like that, and now -216 down here. Well, it looks like there's one x value. And I was hoping you'd take the time to look at 5 times 5 times 5 as a frame of reference. Right? I should be doing minus, minus, minus times, right? That gets us -125. Well, it stands to reason you probably want to look at what -6 times -6 times -6 was. Now, just to see if it was user-friendly. And it was. So the cube root of -216, I believe, is -6. 36 times 6, 6. Carry the 3, 216. Wow, imagine that. So what's -6 times -6 times -6? -216. So if you wrote the cube root of -216, you're not wrong. Okay, so I give you a little credit. I give you a little half a point. Okay, but I was hoping that you'd take some time to think about it a little more deeply. Okay, so odd roots do not have a plus minus in front of it. Even roots, an even root, which is square roots, 4th roots, 6th roots, and so on and so forth. That was an ugly symbol. They have a plus minus in front of them when you do the work. Odd roots, 3, 5, 7. No, one answer. Okay. Oops. Of course, I erased it. Now I don't know what that problem was. So I'll do another one like it. Oh, God. So new problem. So let's put a +1 here. All right. So how do we do that? Bingo, bango, bongo. We're going to take the shortcut. We've looked at why it works. Write the parentheses first. So keep making the same mistakes. At some point, that has to stop. All right. So bingo. 4x plus 1 times 3. Everybody's capable of that. 12x plus 3. Bango. 5 times 5x plus 1. 5 times 5x plus 1 is 25x plus 5. Now we might stop making the sign error that I keep seeing on every test. All right, and 15 here, of course, common denominator. So what's our final answer? 12x minus 25x minus 13x. 3 minus 5, in this case, minus 2. I know it's not the same as what I originally asked, but I don't want to stop the video. And 5 times 3, 15. So that's how you would have done this one. Okay, I'll be more careful with my eraser here. All right. Still concerned about sketching. Y plus 4 equals 2/5 x plus 7. So I'll state it one more time. if you're able to look at this and say, name 3 points, which most of you are now. Most of you are. I can put the +4 on the other side, make it look more like what we've been working with in class. I hope you can see -7, -4. I know most of you can. Maybe we picked up a couple more on the last test. We'll see. Change your x's by 5, -2. Up 5 again, 3. Change your y's by 2, -2, 0. Everybody should be able to locate 3, 0 on a Descartes map. All right, René Descartes Cartesian coordinate system. -7, -4, just estimate, -7, -4, we'll call it here. -7, -4. All right, and horizontally, let's go back 2 and down 2. Oh my goodness. Boy, 2 points on your next test. For those of you who can't do that yet. And would you please label some, I don't care if you label this A, B, C, and then go here, A, B, C. It's easier to, show it that way, then show it that way. But I'm hoping by if you can't do this by midterm, I'm going to be a little conservative. All right, so let's start working on that. Let's not skip it. I know it's at the end of the test, but a lot of you are finishing before the period's over. And I'll be really looking for this. All right, if I don't see change on Friday, maybe I'll recognize that you're not looking at the video. Let's hope not. Let's hope that's not the case. All right, so now we're going to look at -2x squared. Okay, I immediately know that. All right, -16x. I immediately know my zeros on this side. And we've talked about y in class. I'll be happy to talk to you individually about y, but I'm not going to continue repeating the same lectures over and over and over again. Okay, so +3, that's given. The only thing I need is the vertex, and then I have a graph. And I suppose I can get the symmetric point over here as well. I also have the roots as soon as I get this. So what am I looking for? I got to write the +3 here. All right, so I know it's a negative number, so I just divide 2 into 16, 8, put a 4 there. All right, but -b over 2a. We talked about why that is, what it is, and how it works. 16 over -4, that confirms that the x value is -4 at the vertex. So I drop a -4 in. -4 times -16 is 4 cubed, which is +64. So this is -32 without even looking. Yes, -4 squared, 16 times -2. Yes, indeed it is. All right, and we cut this. I'm sorry, I said positive, right? Negative times this, but I wrote a negative. Okay, so there we have our opposite 2-to-1 relationships, and now we're good. Cut this in half, 32 + 3 makes that 35. All right, now I could be making a careless error here as I go along. I'm finding that, getting up there in age, and as I'm talking to you and doing problems, I find that I'm making more careless errors as I get older. But also trying to do it quickly so that you have something to look at. All right, so let's just verify this another way. How do I get from 35 to 3? I go down 32. What's the squared change from -4 to 0? Well, the squared change is 16, right? So -4 for an x to 0. I'm looking at quadratic change. I can see the linear change is -4, but the quadratic change is 16. And what do you get when you divide -2 by, oh, some kind of coincidence here. Okay. That's on your test too, how to do that. What isn't on your test is picking up the marker way over here. There we go. Okay, moving right along. Next graph. Oh, we got ourselves a little exponential. 5 to the 2x minus 7 equals y. Okay, so usually this refers to time. Most exponential functions are, a lot of them, and amounts. Because we're going to do the inverse later, and we're going to go amounts to time, and that's a logarithm. But right now, we're going to sketch this. All right, the constant, cat, K-A-T. All right, it's -7. Boom, 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 boom. Y equals -7. Bigger than 1. I'm growing. And my differentials are going to be at a 2-to-1 ratio if we pick the correct values. So I'll start here, here, and here. I'll get you 3 points. I think we can just count. I think we can probably recognize that we want 2 to the 0. Very important concept, right? Because I create what number? The number 1. All right, so my first differential is 5, my next one's 10, and my next one's 20. Some of you are still saying 5, 10, 15. I'm assuming that you've had some experience with Algebra 1 where you get drilled with a linear function and you think everything's linear. Well, this is not. Okay, this is the basis of this is 5 times 2 times 2 times 2, and I'm discriminating in the positive direction because if I go in the other direction, I'm cutting in half, run out of room. Half, 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 and that's what is bringing this to the asymptotic behavior of -7. In other words, my x's are changing a lot, but my y value is starting to approach this number, and I can get as close as I want to that. All right, so that's what's going on. All right, so what do we want? We want numbers like 0, 1, and 2. They're the easiest to work with. 2 to the 0, 1. 1 times 5 is 5, minus 7 is -2. So 0 gets me -2, and lo and behold, if I add 5 to -7, oh, I end up there. What happens if I add 10 to -7? I should end up at a 3. Let's find out if that's true if I put a 1 in. So what's our function? 5 to the 2 to the x minus 7. I'm hoping you understand how the mechanics of that produces -2. And I hope you understand how the mechanics of that 10 minus 7 gets you 3. Okay? And I should have put an even number here, cut it in half so you could have seen what -1 was, but well, we can do it. Half of 5 is 5 halves minus 14 halves. 5 halves minus 14 halves, get my head in the game. Minus 9 halves, I believe, but really it's 5:30 in the morning, and so I'm not going to say with the exactitude that I didn't make a careless error. So pushing a 2 in here, 4 times 5, 20 minus 7. 20 minus 7 is 13. Oh, that went up by 10. That went up by 5. That's going to go up by 20. That's going to go up by 40, so on and so forth. Right? And so this is a mess. So let me just clean it up real quick and do it again. And I'll give you a rapid fire 5 on that in the next few days, where you get to do 5 of these in a row. So this is what it looks like. Y equals -7. I'm just going to do 2 points where I can clearly see my first differential is that 5. My second differential is 10. Boom, that looks to be 2 to 1. What x? I want my argument, which is however complicated this is, I want it to be 0 and then I want it to be 1. It's not hard to make it 0. There's nothing else going on there, no other part of the calculation. And it's not hard to make it 1. 2 to the 0, 1, 5 minus 7, -2. Yes, that plus that. This is going to go up 10. And so now we've got 10 minus 7 is 3. I can see -7 plus 10 is 3. Right? So I've got that. You shouldn't be showing those differentials eventually, the training wheels. And that's your graph. All right. Now we're going to do the inverse. We're going to go from amount to time, which is a logarithm. All right. The one I gave you was 1947 plus 2 log base 3 x minus 5 plus 7. We're going to create a mantra as we do these for the rest of the semester, where we take the parentheses, x minus 5 over 7, and we set it to 0. We do x minus 5 over 7. We set it to 1. We do x minus 5 over 7, and we set it to the base of the logarithm, and the base of the logarithm in this case is 3. That is going to unlock this problem so that it becomes a 10-second graph. All right. Now, in the exponential, ab to the x plus c, that's the general form for exponential functions. C is the asymptote and it's horizontal, which means that if we're doing the inverse, we have a vertical asymptote. We have a domain restriction. Logarithms work on amounts. Okay, amounts, population, bacteria in a petri dish, half-life of radiation, right? There's got to be something there. There has to be something there. This has to become a positive. Right? I only am allowed to take logarithms of positive numbers in the parentheses. So therefore, x minus 5 over 7 has to be greater than 0. And I hope you can see right off the bat, if I put a 5 in it, this equals 0. So I have to be bigger than 5. So where do you look for the number 5? Oh, geez, it's in the parentheses. It's critical. All right, so the domain is I need to put inputs that are bigger than this number, or you're not going to see any part of this graph to the left of the dotted line. All right, so that takes care of your asymptotic behavior, which means that as I get closer and closer to 5, my y values are going down like the dickens. And we haven't looked at that yet. We will. We'll look at that soon. We're just trying to get these conversations going. So this is the inverse. Now, do I still have that drawing over here? No, but I can make it quicker. All right, so let me do it really quickly here. Just give me a moment. All right, I hope this can be seen. So that's an exponential growth function. If I switch the x's and the y's, God, I didn't do it too well with this paint. Okay, I guess you can see it. There's the asymptote, and there's the trajectory. Okay, maybe I can do it on both sides of the paper so you can see. Because that's how you get inverses. You switch your x's and your y's. All right, so here's your exponential growth. Yep. And now I'm going to flip it. Right? And there's your inverse of exponential growth. Okay, so that's what we're actually looking at. Didn't do that too well. All right, so multiply by 7, add 5. 12 should be critical. And by God, how far is it from 5 to 12? There is a differential there. It's not vertical anymore, but it's a differential of 7. Geez, I wonder where I might spot that up here. Can't imagine where I might spot that up here. Oh, well, so 12 minus 5 is 7. So what do I get when I do make that a 1? I get log base b of 1. Okay, because I really don't know the base yet, right? But I hope some of you know what that is and can help your classmates, right? That's a 0. Why is 0 good here? Because we're doing multiplication. And 0 times anything is the easiest multiplication you can come up with, so it's user-friendly. And it gets me 1947. Okay, I had a student who graphed these logarithms in 4 seconds. He always would challenge me, see if, I got a lot more experience than that student. That's about 20 years ago. All right, but there's patterns here. So I think if you make this a 1, you get the constant. I think we're going to add 2, and I think we're going to get 1949 over here. Of course, let's figure out what makes this a 3. 7 times 3, 21 plus 5, 26. 26. I wonder how far 26 is from 5. Oh, by golly. 26 from 5 is 21 units. Wow. I wonder what the ratio of 21 to 7 is. God, I think there's lots of clues here that you can look at from different perspectives to make sure you're right. Interesting. All right, so let's put a 26 in and do the math. 26 minus 5, 21. 21 divided by 7 is 3. We've been practicing this now for 3 weeks, 4 weeks. I hope everybody knows the exponent you put on top of a 3 to get a 3 is a 1. 2 plus 1947, 1949. All of these numbers are really hiding here. And I don't want them to be hiding from you. So we're going to practice them for the rest of the semester. And hopefully when you get to the next level, you will have done it so many times, you remember how to do it. So that if you have to work with it, when hopefully you do get to a calculus level and start to see how math starts to, study relationships in the real world, you'll be equipped to handle it. That's our goal. All right, enough of that. I'm on a roll here. Haven't even had my coffee. Ta-ta.